Alright, you all. So I'll be doing some electrodynamics problems. Everything seems to be okay with the audio. I'll check and make sure everything is fine. And I may have enough time to do 5. We'll see how that goes. And I'll let you know which ones I'm completing. Like my page refreshed or something. So let me open this back up. Right. So this will be from Pollock and Stump, an old textbook. And 14B. And it says prove that the covariant equation partial J U over partial X U or mu equals the divergence of J equals negative partial derivative of the momentum over time. So we'll be checking this out. So this can be simplified as partial with a lower mu J upper mu, and it should be equal to 0 even though the text doesn't mention it. And J mu would be the 4 vector of uh, the current density. I guess that would be, which is density times C, Jx, Jy, and Jz. So essentially all we have to do is take the partial derivative of this each indices, matching the indices with the uh, respective term in the current. So should be easy enough. We have the first term is the partial derivative over t 1 over c, and that'll be of tc plus partial derivative of x of jx plus partial derivative of y of jy plus partial derivative of z of jz. The c's here will cancel. We end up with partial t plus x plus partial y plus partial z equals 0. So this is the divergence of J. We have all of the Bell operator terms multiplied by each of the vectors of J and summed up. And this just remains what it is. So if we bring that to the other side, we do end up with the gradient of the vector j equals negative partial of the current density. I think that would be. So we prove that. The next one will be 1215, which is a bit more difficult. So 1215 says verify the temporal component mu equals 0 is the gradient of the magnetic field equals 0, and verify the spatial components of the curl E equals negative the partial derivative with respect to time of the magnetic field. And we're to use this, forget what this is called. So this is one of the forms that we can utilize to get uh, Maxwell's equations in a relativistic framework. The other one, I can't remember off the top of my head, but the default uh, tensor is going to be 0, x over c, y over c, z over c, and then the negative of that on the opposite column. The, the diagonal will have a bunch of zeros, and we have should be the default tensor, which is not this one. The other tensor that goes with that, we basically reverse these. So for the G1, the magnetic field is on the outskirts. And the electric field is in the center for the G1. And negatives here. So the default one in the bottom left corner is the majority negatives. So these are the tensors that we utilize in these configurations to output the uh, Maxwell's equations. Let me check and confirm I have everything right. I believe this one is called F. So that one is called F. And so far everything looks good. Except for that one is called F and not J. I believe if we swap the negatives in these sections, we will get the same answer in the end. Uh, because they're sort of mirrors of each other, but let's to get it right. So they want us to use mu equals 0. So we looked earlier that we can sort of simplify this. The column has this high. So this is the same thing as this. And we want mu equals 0. So this would be, and this is Einstein notation. You can look at the relevant coordinates for these. So partial derivative with respect to 0 is always going to be 1 over c, partial with respect to t. And that's the coordinate for the 0, 0. So that's 0 plus partial derivative with respect to x and GO1. So that's row 0, coordinate 1. So that's here. That's bx. With respect to y, row 0, column 2 is there. And partial with respect to z, row 0, column 3 is there. So that gives me with respect to x plus, also with respect to y, the y term equals 0. And of course, that is the divergence of the magnetic field. We do end up with the equation they wanted us to find, and that's for mu equals 0. Now to go to mu equals 1, 2, 3, and I'll copy this down. We have mu equals 1. Then we're dealing with this. So it's going to be 1 over c, also with respect to t. And actually, hold up, let me write out the indices first. That's partial 0, g1, 0, plus partial 1, g1, 1. plus partial 2g 1 2 plus partial 3g 1 3. So partial of O is always 1 over C, also with respect to T. And this time we're going to the first row, 0 column. So that's here. So that's negative the x plus partial with respect to x. First row, down 1 row over 1 column, column 1. So that's 0 plus partial with respect to y. And now we have row down to row 1 over to column 2. So that's minus EZ over C. And then we have plus partial Z of row 1, column 3. That will be here. So we have EY over C. So this ends up being 1 over C. Let's say negative 1 over C partial EX over T. And we'll go plus 1 over C, 0. So we'll say partial EY over partial Z minus partial EZ over partial Y. Then we do mu equals 2. It's going to be partial 0 G 2 0 plus partial 1 G 2 1 plus partial 2 V 2 2 plus partial 3 G 2 3. So then we have 1 over C partial with respect to T. And now we're moving to we're down to the row 2. So it's the third row, but it's 0 1 2. Column 0, which is the left column. We have negative by partial with respect to x of the down to the second row or indices 2 row, indices column 1, EZ over C plus 0 plus partial over D. And now we're at down indices 2 column 3. So that's negative EX over C. So we have 1 over C partial and negative 1 over C partial by over partial with respect to T plus 1 over C. And we have is Z better, partial with respect to Z over EZ with respect to X minus partial that with respect to Z. And The last one, mu equals 3, same configuration, but now the mu here is 3. So that's going to equal partial O G 30 plus partial 1 G 31 plus partial 2 G 32 plus partial 3 G 33. So we end up with, and it has a negative on it as well, negative 1 over C partial BZ with respect to T plus, looks like I'm skipping a step. Let me keep my same configuration going. So that was this one. And we have also with respect to X, to B, indices 3, row indices column 1. So that's negative EY over C plus partial Y, row indices 3, bottom row, column indices 2, ends up being the third row, EX over C plus 0. So that gives me the equivalent. And I'll go ahead and write this one the same way as the others. Plus 1 over C, and we'll say partial EX over partial Y minus partial of EY with respect to X. So if we look at this, oh, and this equals 0. Well, after putting them together, they equal 0. So if we look at these first terms here, we can combine those. That'll be negative 1 over C. And if we sum those together, that'll be the gradient of B. The partial. What do they want us to get? Respect, since it's respect to time, it ends up being just, let me put it like this. So I'm going to extract the 1 over C, the X over the T, Y, B. So that's negative 1 over C and partial with respect to T of B. And then we have plus so we look at this. We have I will have a cross product. See that the I component is going to be partial y ez minus partial z ey. Look at this one. We see that is what we have, but it's reversed. So instead of partial z ey being subtracted, partial y ez being subtracted, and partial z ey is the positive one. So it's reversed. And the same thing here, if I did the j one, that'll be partial z ex minus partial x ez. And we see that partial x ez is the positive one again. And k would be partial x ey minus partial y ex. And we see here the same thing is reversed. So we do have the cross product of e, except it's reversed. So I could say negative cross product of e equals 0. And it's all still divided by c. So I can move one of these to the other side and say negative partial b over partial t equals the curl of e. And since they're both divided by c, when it's on the other side, the 1 over c's cancel. And then we have the equation they wanted. So that's that one. And confirm the audio and everything is working fine. Okay. And thankfully the audio wasn't doubling up, as far as I can tell at least. Right. So we'll go ahead and go to the next problem. Next one is 12.16. And A says from the requirement that we have a Lorentz vector in the form of CPJ, which equals CPJX, JY, JZ. Determine the Lorentz transformation of P and J. So we know that the transformation tensor or matrix is going to be gamma, negative gamma, B, 0, 0, negative gamma, B, gamma, 0, 0, and 0, 0, 1, 0, 0, 0, 0, 1, and V equals V over C. And so if I wanted to transform this into the prime or boosted prime, I would multiply the tensor by the original one. So that's going to be gamma, negative gamma, B 0, 0, negative gamma, B gamma 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 times E, JX, JY, JZ. And I could just multiply this out. So this will be C, JX, JY, and JZ. So that's going to equal gamma CP, a rho, minus gamma BJX, minus gamma BCP, plus gamma JX. And this is still JY and JZ. And to convert this to the other form, all we have to do is change the sign of the velocity component. So that'll be gamma C rho plus gamma BJX. Because remember that beta is V over C, so that's where the velocity is. And this is, we have to swap everything. JX equals gamma beta C rho. Make that positive. Gamma beta C rho plus gamma JY, excuse me, JX, and JY is still JY, and JZ is still JZ. So be it. But it seems there's a detail that's not there. Let's see if I can recall it or just look it up. So just write this out. You'll be rho equals lambda rho in the boosted frame plus gamma beta over c jx in the boosted frame, and j would be gamma beta c rho plus gamma jx jy and jc all in a booster frame. Oh, let me see if I missed anything. So we transform this by multiplying it by the tensor, and therefore we have that. That looks right. Uh, Convert it to the other frame. So that's when we take and put a negative on all the velocities. So we have that. It becomes a positive. Everything in the top becomes positive. So that's that. And then they gave us some conditions. Oh, no, that was a part B. So that's why I'm thinking I need to do something extra. So this is part A and part B. So this is the answer we needed for part A. So we do have those in the other frame. And then part B says suppose frame F prime rho is non-zero but J is zero. J in the prime frame is zero. So that means that we'll end up with, so basically rho equals not zero. J equals Jx, Jy, Jz equals zero. So that equals 0, 0, 0. So all those terms is going to equal 0. So that means that rho equals this, because the Jx term is 0. Then we have J equals, and everything else is 0. And this is for part B. P and J in the other frame. So that's P and J in the other frame. Hold up. Suppose P and J in the other frame. Okay, so that's that. And it says show that J equals PV. So so this is going to be 0. And I need to show that equals PV. So I didn't leave a term off anywhere. Okay. So if I was to take this and multiply it by AC on both sides, See that the right sides of these now match gamma BC row, gamma BC row on the other frame. So that would have to mean, since those equal, and they both equal either of these, that they're equal. So we can say that J equals BC row. To prove that J equals row V. Okay, so this is BC row, and we know that V equals V over C. So that's V over C times C, so that is V row. So J does equal V row. All right, so that's that. I think that completes this problem. And it says explain why rho is greater than rho in a boosted frame. So if we look here, equals rho boosted over square root of 1 minus b squared. 1 minus b squared will be a small number, which is the square root of be a small number. So this divided by a small number will make it bigger. So since we have to increase rho in the prime frame to have it equal rho in the non-prime frame, rho in the non-prime frame must be bigger. So that's that one. And I believe there's two more problems. 1, 2, 12, 14, 12, 15, 12, 16, and two more problems. I believe that covers that one. And it says, so 12, 17 says, prove the following theorem. If the magnetic field equals 0 in F, then the magnetic field in the boosted frame equals negative V cross product E boosted over C squared in any other inertial frame that's boosted. And V is constant in F, and of F with 2. And V is constant of F with respect to F. So what we have is we have one frame F that's sitting there, and we have another frame F prime, and this frame is moving at a certain velocity, we're in the F frame. So something in the F frame seems to be stationary in its own frame, but the entire frame is moving. So we can say that this is an object here and is moving at a constant velocity or rate. But if you look at the object itself, it seems to not be moving with respect to itself. Now with this one, we have to use some different equations. So this is going to be the electric field in a boosted frame equals the same thing, parallel. The magnetic field in a boosted frame equals the magnetic field parallel, and E in a boosted frame perpendicular equals gamma E perpendicular plus V curl of B perpendicular, and B perpendicular equals gamma B perpendicular minus V cos E perpendicular over C squared. Right? So that's that. And this velocity here, I'm used to drawing it in the x direction, but it could be any direction. We just know that it's moving at a constant velocity, and whichever way is moving, it would have a s component or a parallel component, and it would have a perpendicular component. So those are the two components of the velocity, no matter which direction it's going in. We could break it into those. So to swap these, hold up, it's saying that b equals 0. So if b equals bx, by, c equals b parallel plus b perpendicular equals 0, then we have e boosted equals e, and b boosted equals 0. We have e perpendicular boosted is gamma e perpendicular, because this is a curl, so it's going to be v curled with 0. And then we have b boosted perpendicular equals gamma negative v cos e perpendicular over c squared. So we have that. We want b in the boosted frame. So b equals b parallel plus b perpendicular. It's going to be 0 plus gamma negative v cos e perpendicular over c squared. I need to replace this e perpendicular with something. The detail is It didn't seem intuitive, but I'm going to solve for E perpendicular here. There's no V to this turn it negative, so no V to swap, so solve. So E perpendicular equals E boosted perpendicular over gamma. So this is going to become gamma negative V cross E perpendicular boosted over gamma C squared. And that will be needed to solve for. It say it's going to be in boosted, so that's why we have to get the boosted in there. And when we have a cross product, so we have alpha x cross y. That's the same thing as alpha x cross y or x cross alpha, which means that I can take this 1 over lambda and extract it. So that's going to be gamma over gamma by extracting out the gamma in there. V cross E boosted perpendicular. So that's going to be negative V cross E boosted perpendicular. I left off my C squared. C squared is still there. E boosted perpendicular over C squared. And that is all of B. So B in the boosted I should actually call this S for B boosted. Boosted, boosted. And I substituted the B boosted what they stand for. So B boosted is B boosted per parallel perpendicular. Substituted what those are. I have to solve for E perpendicular to get everything in the boosted frame. Since there's no V to just swap it over. Then I input that. Use the property of cross products that one of the uh, constants on one of the terms is multiplied by the whole thing. I can pull that out, that becomes 1. And that is what we were looking for. And I believe the V is constant thing was just pointing out that V is constant. So I think that's the whole thing. So that's that. The last problem, 1218. It says in 1952, Einstein wrote, would let me more or less directly to the special theory of relativity was the conviction that the electromotive force acting on the body in motion, magnetic field is nothing else but an electric field. Be more or less directly to the special theory of relativity was the conviction that the electromotive force acting on the body in motion and a magnetic field was nothing else but an electric field. Right? So he actually his understanding and studying delving deeply into electrodynamics is what led him to special relativity. So electrodynamics was the foundation of I guess you could say the arena within which he developed the special theory of relativity, how these forces interact with each other when charges and things are in motion, and the relative um, frames by which we can describe the same interactions. So it says, suppose in an inertial frame F, there is a magnetic field B, but the electric field is zero. If a charge Q moves with velocity U in F, so we have our frame F, it's just sitting there. We have a charge Q in its own frame. The charge Q moves with velocity U. So this is moving with velocity U equals UI in F. And it experiences a force F equals Q U B K, a magnetic force. F is the rest frame of Q. We have that there. Find E and B, the fields in F prime, right? So I believe we have to use the same equations that I have not memorized. Let me get these. So we have E boosted parallel equals E parallel. B boosted parallel equals B parallel. E boosted perpendicular equals gamma E perpendicular plus V cross B perpendicular. And B boosted perpendicular equals gamma B perpendicular minus V cross E perpendicular over C squared, right? So that's that. I'm sure these equations are given normally. We want to find E and B in the F frame, I mean the boosted frame. So um, E boosted perpendicular would be gamma E perpendicular to B or E is all 0. So that's going to be B cross B. Since E is all 0, which was given. And B is only in the J direction, only the J direction. And this is only the J direction. J must be perpendicular. So that's gamma V cross B J. Because we have a B, it's only in J, and we know it's going to be perpendicular. Or it's only the perpendicular component matters. And we could assume that's in the same direction, especially since the velocity is in x. So we have that. We know that velocity is in x. So we can actually input the velocity as well, ui. So that's going to be gamma u b sine theta k, because I across j is k. That's going to be gamma u b k, since the angle between I and j is 90 degrees. So we have that. And b in the boosted is going to be gamma. Again, E is all 0. So we have gamma b perpendicular. So this is going to be gamma b j. I believe that's it. Force on Q and F prime. Check my fields first though. E is gamma UBK, so that's right. And B is gamma BJ, that's right. See, this equals E boosted, this equals B boosted, since the other avenue is 0. E is 0, so there's no E parallel, and B is only perpendicular. There's no B parallel, so that works out. Let me remind myself that we don't need these. And so that's that. And to get the F force, remind myself, remember the force one. Look this up here. To do A. So I have to get the force. So all I have to do is get E prime and B prime, which I wrote elsewhere with the little squiggle. Right. So that's that. So hopefully that was helpful or at least entertaining. And I'll be back probably next time with some quantum problems. So look for me. All right, y'all. Have a good one. Like, subscribe. Darrell Berry Jr. on my STEM channel. I'm out.